Hello, and welcome to the Raised Beaches podcast, a podcast about paleoclimate and global change. I'm Dr. Evan James Gowan, but you can call me Evan. This is episode 3 of the Raised Beaches podcast, and I'm recording this on October 30th, 2024. Today's podcast, I'll be talking about the hurricanes that have tragically hit southeastern United States, a paper about sea level rise doubling in the rate of sea level rise doubling in the past 30 years, and a global coastline data set. In this episode's deep dive, I'll be discussing about proxy records, and I will talk about 3 papers. One will be on methane fluxes in Beringia. Another will be on paleo sea level changes in northwestern Canada. And another one will be on Phanerozoic climate changes. So Phanerozoic covers most of the past 500 million years. So that is a very interesting paper. So it's October, very late October, and Japan, the autumn is coming very slowly. So today it was a bit cooler, but last weekend I went to this town called Misato, which is located in central Kyushu, which is the island that I live on. And driving around there, none of the trees have started to change color, which is quite unusual, I think. And it's been because the summer is so hot. It's basically delayed the start of the autumn. And they are really not expecting the colors of the trees to change to their autumn reds and yellows until well into November. So yeah, it's just another sign that the climate is changing here in Japan, that the autumn is getting delayed. And another thing that I did in October, so in Japan, there's a long weekend in mid-October called Sports Day. And because it's been so hot, my wife and I said, well, we better hit the beach. It's nothing I like better than the beach. And we went to Nagasaki close to this town called Sasebo. And of course, when I go to a beach, I want to explore the geology a bit. And so the rocks at the beach we're at are Miocene in age. And sort of the earlier part of the Miocene, so around 18 to 22 million years old. And I picked up one of the rocks. So if you're watching the video version of this podcast, you'll be able to see my rock. And anyway, so this rock, the bottom part of it is sort of a medium grain sized sandstone, and on top it's very abrupt change to this very shell rich, maybe you could call it a coquina, because it's a large part of it is shell fossils, but it's still got the same kind of sand in it. And walking along this beach, you could see this transition in the bedrock from this medium-sized sand to the shelly layer, and the abruptness of it, and the fact that the matrix is, or there's still this sand within the shell layer. It makes me think it's probably a storm layer, and there was also kind of this pyroclastic flow material in the rocks as well, so makes me suspect that there was a volcano nearby. And yeah, I looked up the geology of this area near Sasebo, and basically it was a coastal area that was uplifting, probably, and this was during the period of time when the Sea of Japan was starting to form. So that was pretty interesting to see. Another thing we did in Sasebo, we took this cruise around these islands. So there's these little islands everywhere because the landscape is basically a flooded river valley area, because which formed when sea level was lower. And you look around these islands and you can see there's like these terrace levels that are above the high tide level. And it's a sign that at some point the sea level was a bit higher than present. And looking at the museum that they had there, they suggested this was during the Holocene, mid-Holocene, so like 6,000 to 7,000 years ago. So sea level dropped after that point in time. And this area, I don't think, is uplifting. So I don't think tectonics are really responsible for that relative sea level change. So I've talked about this in the previous episodes about ocean siphoning, and this is probably a result of that there's been a bit of a sea level drop due to the water going back towards where the northern hemisphere ice sheets used to be. So the really big weather story that's happened in the past month are that there were two major hurricanes that have hit the southeastern United States, Hurricane Helene and Hurricane Milton. And this is being driven by the fact that the ocean surface water temperatures in the Gulf of Mexico are very, very hot. So this has allowed these hurricanes to develop very quickly and also to get very powerful. As an example, Hurricane Milton explosively intensified, and the central pressure went below 900 hectopascals. So that just the pressure can give you an idea of how powerful the storm is. And in the Pacific, we have typhoons, which are the similar kind of storms. And it's not so uncommon to have the pressure for typhoons to go around 900 hectopascals, but in the Atlantic, it's pretty rare. So Hurricane Milton is achieving a central pressure below 900 hectopascals is quite remarkable. And it was a very powerful storm, and I really sympathize for all those who are affected by these disasters. And it is a reminder that areas in that region are very vulnerable to these hurricanes, which seem to be getting stronger as time has gone on. And the likelihood of these kinds of disasters is going to increase because the surface ocean temperatures are increasing. And one place that was affected that's relevant to paleoclimate was the National Centers for Environmental Information, which is basically a center within the National Oceanic and Atmospheric Administration in the United States, which stores data related to climate and of course paleoclimate as well. So the description, the National Centers for Environmental Information, is also known as NCEI. And NCEI maintains one of the most significant archives on Earth with comprehensive oceanic, atmospheric, and geophysical data. We archive over 229 terabytes of data each month from over 130 observing platforms. And so this center is located in North Carolina, which was affected by Hurricane Helene. And of course, I really feel bad for all the people that were affected by the hurricane, and the center was down for several weeks, and they worked very hard to get this back up, because the information stored on these servers is used for weather forecasting, for instance. This is not the first time this center's gone down. I remember during my PhD, the NCEI went down due to the government shutdown, and of course that's a man-made problem. And we have to think that these government organizations that hold this valuable climate data are vulnerable to political changes. So we all know that there's this big election next month, and it's my hope that the results will be favorable, so that the NCEI will not be vulnerable to shutdown. And when the government shutdown happened I think it was in 2013, the Internet Archive was backing up a lot of this data, but the Internet Archive itself in the past month was hacked, and it just goes to show that there are actors out there who do not like the fact that this information in general is available. So it's not a great time right now in climatic information is vulnerable to meddling from governments who don't like what it says. The next bit of big news that happened in October was the release of a paper by Hamilton et al. And this paper was called The Rate of Global Sea Level Rise Doubling During the Past 3 Decades, and it was published on October 17th in the journal Communications, Earth and Environment. And what this paper did is that they looked at the satellite-based measurements of global average sea level. And I talked about this in episode 2. And the authors of this paper are kind of responsible for maintaining that time series. And coincidentally enough, there's been 30 years of measurements, and that's usually kind of a baseline in climatic data to sort of be able to think about averages and like as a baseline. And basically what they've done is they've calculated whether the rate of sea level rise in the past 30 years, which is around 10 centimeters, whether that rate is changing. So if it was just a linear change, you would just see a flat line. And in some ways, you look at the data, and it does kind of look linear, but I think the past 5 to 10 years, the rate has been increasing. That's something you can see in the annual measurements. And anyway, the rate around 1992, they said, was about 2.1 millimeters per year, and now it's 4.5 millimeters per year. So the increase in sea level is being driven mainly by 2 things, and that's the ocean water is warming up, and the second thing is that glaciers are melting. And if you look at the time series, it's not smooth. There's like up peaks and troughs, and I remember during my PhD there was a big trough, and that was related to a large flood event that happened in Australia. So there was so much water in this flood event that came out of the ocean that it caused global average sea level to fall for a while. But, it's a flood event, so that water eventually went back into the ocean. And anyway, this paper is kind of just an update, and most people who are involved in investigating sea level changes are aware that the sea level rise rate is increasing. So it's kind of an incremental paper, but nevertheless an important paper to communicate the fact that sea level is accelerating. And in the end of the paper, they sort of extrapolated what they think the sea level rise will be by 2050, and they estimated that there'll probably be about 20 centimeters of sea level rise in the next 25 years, which, that's like 3 times higher than the amount of sea level rise in the past 30 years or so. The last thing in this introduction I'm going to talk about is the global coastline data set. And this is called the Global Self-Consistent Hierarchical High-Resolution Geography Database, or GSHHG. Yeah, that's a bit of a mouthful, even for me. And this data set was originally created in the early 90s by Paul Wessel and Walter H.F. Smith. And Paul Wessel and also Walter Smith are most famous for creating the generic mapping tools, which is a software tool set that allows you to plot and analyze geospatial data. And I'm not exaggerating when I say Paul Wessel is one of the most influential geophysicists in the world. And unfortunately, he passed away earlier this year. But his influence on geoscience has been immense. And anyway, the GSHHG consists of three sort of data sets. One is the world vector shorelines, the C, which is the shoreline data, the CIA World Data Bank 2, which contains the lakes, the rivers, and the political boundaries. And they also use the atlas for the cryosphere for Antarctica. And anyway, the last update of the GSHHG was in 2017. And I've found this to be a bit problematic for my work. So last year I published a paper on paleo sea level changes in Greenland. And one of the things that I was doing was plotting up where the data were located on a map. And all I had was this GSHHG on the map, which was showing the outlines of the coastline of Greenland. And what was happening is that these data points were not showing up where the shoreline was. They were being plotted way out in the ocean. And I'm like, this doesn't make any sense. And the person who collected this data, Sven Funder, I emailed him. It's like, this doesn't work out. And he's like, we measured where these data were with a differential GPS. The location should be correct within a few centimeters. And so I was scratching my head, and then I went further and plotted the topography data set. And so the topography, the data points were in the correct location. So the problem was the coastlines. And if you look at the coast, where the coastlines are versus where the topography is, and in some places it's off by 40 kilometers. And so yeah, anyway, I submitted a bug report, and Paul Wessel responded, and he said, well, yeah, we know that the coastline is problematic, but I don't have time to fix it right now. And this is very problematic because lots of things use the GSHHG in their products. A good example is Google Earth. So if you zoom into northern Greenland, you'll see that these chunks of ice that is where the island should be. But that's since the coastlines are in the wrong place, the islands don't show up. It shows the ocean, which is covered in ice. So you'll see that the satellite imagery is sometimes cut off because the coastline is in the wrong spot. So this is a consequence of these errors in the GSHHG, and it can be very visible what happens if you're relying this when you are georeferencing your database or your data sets. And the way that I fix this problem, at least for my Greenland paper, was that I created a shoreline by basically taking the topography data set and drawing a contour where the elevation was 0. And for Greenland, that works okay, I guess. But you could not generate a coastline everywhere using this technique, and this is because in some places things are very flat near sea level, and a good example is in the Jiangsu province in China. If you look at the topography database, since the land is so flat, you can see artifacts in the topography data set where it fluctuates between within a few meters of sea level. So if you were using a contour of the 0 elevation mark, the coastline would not be in the correct location. And this is really something that needs to be done manually. And of course, you have to think that the coastline itself is not necessarily going to be constant, especially since we have sea level rise. And for someone like me who looks at broader scale things, this may be not such an issue, but ultimately this global data set of coastlines is probably used by a large proportion of people who make maps, and it's not necessarily accurate, and most of this data were derived from topography maps that were drawn, decades ago. And obviously, this should be updated, but nobody's doing it. And you'd think, well, somebody should be maintaining a data set of coastlines, because that is important. Especially with lakes and rivers, they've changed through time. But yeah, nobody, as far as I know, nobody's doing that, and I think that's kind of crazy. I think somebody should be maintaining this data set, and I hope that this does happen at some point. But that seems like a UN sort of thing that should be done. It should be done by the United Nations or some international consortium. But I'm just one person who has very little resources, so I guess I'm not going to be the one who does it. I just don't rely on these coastlines to be accurate, is all I'm going to say, especially in places that are sparsely populated like Greenland. So I have seen people use Google Earth to georeference things, and that's a very bad idea. Like they use they use this coastline data set to georeference their satellite data. So yeah, don't be careful out there and make sure you think about your data. That's my message. So that's it for the introduction. So in this episode's deep dive, we're going to look at proxy records. So right now I'm stepping back a bit from the discussion we had before on sea level, and this is because proxy records are very important when we're discussing anything related to the Earth's past. And this is because in the past, like right now, if we want to know about the conditions on the Earth's surface, we have thermometers, we have rain gauges, we have satellites that are constantly measuring the properties of the Earth's surface. But in the past, we don't have any of that. So we have to rely on so-called proxies. And in this deep dive, I'll discuss about some of these proxies that paleoclimate scientists use. And what a proxy is basically some indicator of the past climatic changes. And it usually doesn't give a direct measurement of things like temperature or rainfall or any other kind of climatic parameter. But because there's usually a relationship between the proxy and the climate, we can estimate what the conditions were like in the past. And there's many different kinds of proxies, and changes in sediments, the chemistry changes in both the sediments and organisms, changes in the abundance of organisms, changes in the accumulation of ice, and even historical records. And in the intro, I talked about the National Centers for Environmental Information, and this is a place where a lot of this kind of proxy data is stored. So it is a very important place that a lot of us paleoclimate scientists rely on. So the first thing which I think is the most important kind of record is sediment core records. So basically, you can go to a lake or the middle of the ocean, and you go down and drill or grab samples of the sediments. So in the ocean, you can drill down like several kilometers and collect a core of the sediment. And basically what you do is you go along the core and take samples, and based on the changes on whatever property that you are measuring, you can make inferences on the past climate. And for deeper time, so times on the scale of hundreds of thousands to millions of years, we use oxygen isotope proxies. Of course, you can also use oxygen isotope proxies for shorter time scales, but I am always thinking on very long time scales. And this is similar to there are other kinds of proxies like this, chemical proxies. So oxygen isotopes is one of the most common ones. So there are two main isotopes of oxygen. There's oxygen 16 and oxygen 18. And oxygen 16 has 8 neutrons, and oxygen 18 has 10 neutrons. So oxygen 18 is heavier, and that changes how it behaves. Like chemically, the different it will form bonds with the way any oxygen would. Like oxygen 16, oxygen 18 behave basically the same, but dependent on the ambient conditions, for instance, temperature, these two isotopes sort of behave in a slightly different way. For relevance to me as somebody who studies past sea level, in the oxygen 16 will preferentially evaporate out of the ocean because it's lighter, and that oxygen 16, when an ice sheet forms, it will accumulate in the ice, and therefore the average amount of oxygen 18 in the ocean increases. So that is a proxy record of ice volume, just as an example. And how we measure that is in the ocean, there are these single-celled organisms known as foraminifera, and these organisms form a shell called a test, which is made of calcite. And basically what you can do is in these sediment cores, there'll be an accumulation of these single-celled organisms, the shells of them, and you measure the ratio of oxygen 16, oxygen 18, and so as you go down the core, if there's an increase in oxygen 18, that means there's probably more ice on the surface of the Earth. And if that oxygen 18 goes down, then there's probably less ice because that oxygen 16 rich ice melts, and that water goes back into the ocean. Another thing that measures is that because the chemical reactions when the foraminifera create this calcium carbonate is dependent on the temperature of the water, and it's kind of in a similar way that as the temperature decreases, the amount of oxygen 18 in the shells increases. So basically, it's sort of a when you look at these oxygen proxy records from the ocean, high oxygen 18 means the water's colder, which makes sense in a glacial period, and also there's more ice. So picking out the relative influence of temperature and the ice volume is a subject of debate. You can also measure oxygen isotopes in speleothems. So speleothems are cave rocks that form when water drips from the bottom or from the top of the cave, and basically the calcium carbonate forms from this drip water, and the relative amount of oxygen 18 and to oxygen 16 will come from that drip water, and therefore this drip water is derived from rainfall. So you can use these speleothems to determine changes in rainfall patterns, for instance. Another proxy is corals. So corals are great for making short time scale proxy records, because each year the corals will create a new layer. So basically it grows outwards. And one of the great things about using corals as a proxy record is that if you make very small measurements along these annual growth bands, you can get an idea of the changes in the environment at a seasonal time scale. So the ratio of calcium and strontium is used to do that. So calcium and strontium are different elements, but they're in the same row in the periodic table. So they get incorporated, and the strontium gets incorporated into the calcium, and that is dependent on the temperature. So the ratio of calcium to strontium provides a very precise way to define what the ocean water temperature was. And as an example, in Kikaijima, which I talked about in episode 2, there's been a lot of studies on the the calcium strontium records of these corals, of these fossil corals, and it tells us, for instance, that 5,000 years ago, the ocean surface temperatures were warmer than they are at present. So it can give us a window on what happens when the water temperatures increase. Another proxy record that you often find in sediment cores are biochemical proxies. So one example is lipids or fat molecules, and one of the common proxy records of temperature changes is this index known as TEX86. So there are 5 different lipid molecules that have 86 carbon atoms, and based on the relative amount, and these lipid molecules are created by a single-celled organism known as a Hierarchical. So it's kind of similar to a bacteria, but it isn't a bacteria. And anyway, the relative amount of these 5 different lipids will depend on the water temperature. So, and it's a very linear relationship, at least between 5 and 30 degrees Celsius. So this index is a very precise way to figure out the past changes in ocean water temperature. You can use the organisms themselves as a proxy. As an example, diatoms, which are another type of single-celled organism, they can be used to determine the concentrations of sea ice, because there's certain kinds of diatoms that like to live in sea ice, and certain kinds of diatoms that do not like to live in sea ice. So if you're in a sediment core and you find certain kinds of relative abundances of certain kinds of diatoms, it can tell you if there's a dominant amount of sea ice versus sea ice-free conditions. And this is one way you can use the abundances of organisms to tell you about the past climate. Another really common proxy record are tree rings. So every year a tree will grow outwards and create a ring, and if you cut a log, you can definitely see it. So the lighter colored areas are from the earlier part of the spring and summer, while the dark thin layer is from the latter part of the summer and the autumn. And based on how thick the tree ring is, it tells you something about the climatic conditions of that year. So if you have a thin ring, it's probably going to be a cool or dry season, or if you have a thicker ring, it was wetter and hotter maybe. It depends on the tree species, I think, and where you are, but based on the relative thickness of these rings, you can determine the past climatic conditions. And yeah, I talked about one of those studies in episode 2 if you're interested. Another really big climate proxy record are from ice cores. So basically, you have glaciers and ice sheets, and every year there's snowfall on it that goes on it, and if you have a net accumulation, you can actually see layers in the ice from these annual precipitation events. And in ice sheets like Antarctica, you can have 3 to 4 kilometer thick layer of ice, and it takes thousands to hundreds of thousands of years to accumulate that ice. And if you look at this really old ice, you can see air bubbles in it, and those air bubbles are basically little bubbles of past atmospheric conditions. So we have records of past carbon dioxide concentrations in the atmosphere going back 800,000 years, because we've directly measured these air bubbles in these ice cores in Antarctica. And the ice cores themselves will have other information. So the amount of dust in the ice can give you information on wind patterns, because the dust doesn't come from a local location. It comes from further away. And the chemistry of the ice itself, like, say, for instance, the oxygen isotopes, can give you information on the precipitation, or past precipitation, and that also gives you information on changes to the climate. Another proxy is direct geological proxies, and I've already discussed this, the Raised Beaches podcast. You find a raised beach, a beach above present-day sea level, that indicates that, in a relative sense, sea level was higher than present. And in places that are tectonically stable, that's an indication that in the past, the ice volume on the Earth's surface was less than present. So that also gives you information about the past climate. And the final thing that I'll discuss are historical records. So one of the most famous historical proxy records, at least what I think, is the full bloom of the cherry blossoms in Kyoto in Japan. And there are written records of when the full blossom happened of this particular tree that is in central Kyoto. And the day relative to the start of the year when the full bloom happens is dependent on the average temperatures in March. And why this record is very famous is that prior to 1900, the average start was about 103, 104 days after the start of the year. And then after 1900, you can see there's been a fairly abrupt change where the full bloom is now happening upwards of 10 days earlier than prior to 1900, and that's an indication that the spring in Kyoto is starting earlier than it used to be, and it's a very clear indicator of climate change. And the past few years it's been very early compared to even that average, or the average line. So things are definitely heating up in Japan. So in summary for this deep dive, this gives you sort of a taste on what paleoclimate scientists use as their base data. Like, they don't have a thermometer of the past, but there are ways to figure out what the Earth's past temperature was, for instance. Of course, it's like an incomplete puzzle. Like, it's not possible to get these records everywhere. So you also have to combine it with modeling. And in the paper section, I will talk about one of these kind of studies. And these data are very essential to understand past climate changes. So now a little bit more about proxy records. So my undergraduate degree was in geophysics, and the department sort of had a focus on mining and oil applications. So more of the profit-driven end of things. And because I was taking geophysics, I didn't really have a lot of exposure to paleoclimate while I was a student there, and even in my master's degree, even though I was working on a topic related to paleo sea level, the reality was I was still in this kind of mindset of exploring the deep earth. And it was during my master's when I was first exposed to climate science, really. But I really didn't start to learn about proxy records until my PhD. And there's a good reason for this, because the Australian National University is one of the best places where people are studying proxy records. And as a student, I went there and I participated in the morning tea, and that allowed me to talk to a lot of the people who were working on these proxy records. And there are people working on like coral-based proxy records, there's speleothem proxy records, and of course like lake sediments. And one of the great things about the Australian National University is because it was such an important place for studying earth science, is that every week there would be a seminar, and often these seminars were on paleoclimate proxy records, and I sat in on these, and that's really where I learned about proxy records. So I kind of learned about it through osmosis rather than sitting down and actually learning about it. And during my time at the Alfred Wegener Institute, I was working with a lot of climate scientists, and I'm not, climate modelers, not. And one thing that sort of set me apart in that group was that I actually had a fair amount of knowledge about proxy records, and there I also became more acquainted with different kinds of proxy records and how they can be used to evaluate climate models. And so as a result, even though I never had any formal training on proxy records, I did learn quite a bit about them. And probably the most famous proxy record, and this probably will get a deep dive in a future episode, is the LRO4 curve. And it's called the LRO4 curve because the authors of this curve were Lisecki and Ramo. And the paper came out in 2005, but they had hoped to get it out in 2004, so it's '04. And anyway, what this is it's a stack of oxygen isotope proxy records from sediment cores collected in the deep ocean, and uses 57 of these kind of records, and it allowed them to create a composite record of oxygen isotope changes in the ocean for the past 5.2 million years. And why this was so important is that they were able to create a time scale for these records, and basically it became sort of the de facto standard for the time scale of paleoclimate research. So basically, there's lots of squiggles on this line which represent glacial and interglacial time periods. One of the remarkable things about this record was that the amplitude of these changes sort of got larger as you got closer to the present. So in the past million years, there's been very large amplitude changes, and in comparison to the late Pliocene, so before 3 million years ago, where the variations were a lot less. And the main reason for this change is that you started to get an intensification of glaciation in the northern hemisphere, and that, of course, I talked about how if you increase the oxygen 18, that means that you have more ice on land. And also there were changes. There was a general cooling of the ocean for the past 5 million years as well. So yeah, that is probably the most famous proxy record, and it is sort of the basis for the timing of events, at least during the past few million years. Another thing that came up which is proxy record adjacent, is the JOIDES Resolution had its final voyage over the summer. So what the JOIDES Resolution is, it was a ship that drilled into the ocean and collected these sediment cores. And most of the funding for the JOIDES Resolution came from the National Science Foundation in the United States. And they decided last year that they would stop funding this ship. And the JOIDES Resolution started collecting these sediment cores in 1985, and it was able to operate in a lot of very harsh environments. And this is a very tragic thing when we think about trying to learn about the Earth's past climate. And it should not be understated how much we know about paleoclimate that has come up in the past few decades. It has come from data that was collected by the JOIDES Resolution. Japan and China have their own drilling ships, and they're hoping that it will be able to make up for the loss of the JOIDES Resolution. But I think the general consensus is that these ships will not be able to go to some of the same places that the JOIDES Resolution was able to go to. And there's a nice article about this in The Guardian that came out a few weeks ago, and I'll link to it. But it's a very sad thing for paleoclimate that the NSF felt that it was not worth funding this kind of work. And I hate to end things on a sad note, but it's just how things are nowadays. Is that funding to collect data is very expensive. It's more expensive than creating a climate model, for instance. And I always think about a single data point from a remote beach in Antarctica might have cost $500,000 to collect, and it's hard to justify spending that kind of money just to get some data point in a remote area. But when we're thinking about validating climate models, we need this data. So I don't think that they will restart the JOIDES Resolution, but I'm hopeful that a new ship can be created or built that can replace it. I'm crossing my fingers. So in this episode, I'm going to talk about 3 papers. One will be on methane emissions from Beringia. Another will be on sea level changes in northwestern Canada. And finally, I'll talk about a surface temperature reconstruction of the past 485 million years. So the first paper on methane is titled Methane Flux from Beringian Coastal Wetlands for the Past 20,000 Years. And this is by Fuchs et al. It was published in the November 15th issue of Quaternary Science Reviews. And as a disclaimer, I am the third author on this paper, so this is a bit of self-promotion. So methane, of course, is a very powerful greenhouse gas, and low-lying coastal wetlands, tidal wetlands, are a natural source of methane gases. And in the past 20,000 years, we've seen sea level rise, and the Beringian Shelf is a very flat area, and during the last glacial maximum, most of it was exposed. And when the sea level rise happened, the amount of coastline was actually greater than it is now, and it was hypothesized that in the past, when the sea level was rising, the amount of methane emissions from the coastal wetlands was probably higher. And so Beringia is the area that includes Alaska and eastern Siberia. And right now, there's the Bering Strait, which separates Alaska and Siberia. But 20,000 years ago, when sea level was lower, that area was all land. And gradually, as the ice sheets melted, the sea level rose, and eventually that shelf area got flooded. And that happened between 20 and 5,000 years ago. So Fuchs et al. Used PaleoMist, which is a paleotopography data set that I created, and they wanted to check to make sure that the paleotopography reconstruction from PaleoMist actually reflected the real changes in the coastline area. And so they took sediment cores from the Beringian Shelf, which contain freshwater peat. So the freshwater peat is an indication that sea level was lower than the elevation of that core sample. So basically, Matthias Fuchs, who's the lead author, took this data and plotted against the coastline history from PaleoMist and validated that more or less this topography reconstruction is consistent with these freshwater peat data, so that the topography did not flood, or the reconstruction did not show that the land was flooded before the peat stopped accumulating. And so because we know that the topography reconstruction more or less represented the sea level change history in that region, he used a model to calculate the amount of methane flux from coastal coastal wetlands if the configuration of the coastline was changing during the deglaciation. So based on that, between 9 and 16,000 years ago, it was estimated that the amount of methane from these coastal wetlands was roughly double what it is now. And the thing is, though, the amount of methane being emitted from the coastal wetlands is not really substantial compared to other things like peatlands from terrestrial areas. But one of the points is that although the amount of methane emitted from these Beringian coastlands are not great, the fact is that this doubling of the relative amount of methane being released actually started earlier than the development of these terrestrial peatlands. So it might have contributed a little bit to the global warming that was happening during the deglacial period. Yeah, it was interesting to be involved with that. I didn't know about methane fluxes, so now I know a little bit about it. So I thank Matthias Fuchs for inviting me to be part of this study. The second paper I'll talk about is actually somewhat related because it's on paleo sea level changes and ice sheet changes in northwestern Canada in this area close to Banks Island and the Amundsen Gulf. So the Amundsen Gulf separates Banks Island from the mainland of North America. And they were interested in the history of what went on in that area for the past 30,000 years. And this paper, which is titled Passage and Removal of the Amundsen Gulf Ice Stream, Northwest Laurentide Ice Sheet, recorded by the Glacial and Sea Level History of Southern Banks Island, Arctic Canada, is by Vaughan et al., and it was also published in the November 15th issue of Quaternary Science Reviews. So yeah, if you don't, Banks Island is in northwestern Canada, and one of the interesting things about the history of investigations of Banks Island is that the people who originally went there thought, oh well, this island has been glaciated, but this glaciation was quite ancient, and so they proposed during the last glacial maximum, so about 20,000 years ago, that Banks Island was actually not covered in ice, even though the rest of Canada was basically covered in ice. And a group of scientists based out of the University of Alberta went back there in the 2000s and completely revised the history of the glacial history of the island, and said, well, the evidence we have is that it was glaciated at the last glacial maximum, and that might have been the only time it was glaciated. So it basically very much flipped the script on the history of this island. And this paper by Vaughan et al. is a geomorphology and geology paper, and it's quite long. It is a review paper after all. And anyway, they focus mostly on southern Banks Island, and one of the interesting things they found was that the retreat of the ice from Banks Island had to have happened before the ice stream that was flowing, the glacier that was flowing through the Amundsen Gulf. So they found evidence that there was a lake on southern Banks Island which was dammed by the ice in the Amundsen Gulf, and they found shorelines and deposits all throughout there. And the thickness of the ice could be estimated because the highest point in southern Banks Island is about 720 meters high, and they found what are known as erratics. So erratics are rocks that were transported by the glacier from somewhere else, like far away. And based on what these rocks were, they said, well, this is from the Amundsen Gulf ice stream. And because they found these rocks, they're like, well, the Amundsen Gulf is 400 meters deep, and this mountain is 720 meters high, so the thickness of the ice was at least 1,100 meters. They also investigated the sea level changes, and so on the western part of southern Banks Island, they find evidence that the maximum sea level high stand was 11 to 15 meters, but as you go further west, it's up to 41 meters. And what that indicates is that two things: that the deglaciation happened earlier on the west side than the east side, and that the ice thickness was likely less on the west side, and that makes sense because you're further from the center of the ice sheet. One interesting thing is that the high stand deposits in the western part of Banks Island don't have any fossils in them, so that is an indication that the deglaciation happened before the the Bering Strait got flooded. So yeah, related to the previous paper, that the shells and the marine shells and marine mollusks could not actually get into the Arctic Ocean until the Bering Strait was flooded. And so the oldest shells they found were 12,900 years ago. So they estimate that their estimates that the flooding of the Bering Strait happened about 14,700 years ago. So the deglaciation of Banks Island happened before that. Another thing that they found was that they find shell fossils in the glacial sediments themselves, and these obviously predate when the ice advanced over Banks Island. And based on the ages that they found on these shells using radiocarbon dating, they estimate that Banks Island was not glaciated until sometime after 24,000 years ago. And that's quite late, because the last glacial maximum period started about 27,000 years ago. And they estimate, based on analogs on the mainland across the Gulf, that the maximum extent of the ice might have been as late as 16,000 years ago. So the ice advanced all the way to the edge of the continental shelf off the west coast of Banks Island, and it didn't stay there very long. But based on the thickness of the ice, the icebergs, there are scours on the bottom of the Arctic Ocean at 1,000 meter or even deeper depths, and the thickness of the Amundsen Gulf ice stream was thick enough to produce icebergs that would have been able to touch the ocean floor at that depth. And yeah, it's as somebody who's planning to model the ice sheets in that area, this was a very nice study for my work. The final paper that I will discuss is on a temperature reconstruction of the Phanerozoic, and this is titled A 485 million year history of Earth's surface temperature by Judd et al. And it was published in the September 20th issue of Science. So the first thing you probably asked was, what is the Phanerozoic? And the Phanerozoic is defined as the time period when complex life forms started to appear on the Earth. And by complex, they mean things that have preservable parts, like shells. So prior to the Phanerozoic, the animals and other creatures did not secrete carbonate shells or anything like that. The rise of complex life obviously had a major influence on the Earth, and during the Phanerozoic, the positions of the continents changed a lot. So it's kind of tough to understand the climate changes unless you account for that as well. And so what Judd et al. Did is used a technique called data assimilation. So there are two primary ways that you can infer past climate. You can use the proxy records, which I talked about earlier, and also climate modeling. And the proxy records provide you with a more direct way to understand what the past climate was. However, the issue is that they're heterogeneous. Like you do not have proxy records that cover the entire world. Some of that is because we haven't measured everywhere, but also because the geological record is very incomplete. And the climate models give you a complete record of global climatic conditions, but the issue is that climate models require a lot of computational resources, so they're usually run at a very low resolution, like grid cell sizes on the order of hundreds of kilometers in some cases. And also, climate models are not complete. Like they're missing physical processes in them because we don't have a complete understanding of the climate system. So what Judd et al. Did is use a technique called data assimilation, and this is basically a way to take the climate model output and statistically correct for these problems in the climate model using the proxy data. So it's basically a machine learning technique where you take the climate model output and adjust the climatic fields using the data and iteratively create sort of an uncertainty range of what the climate was. So the data that they used were proxy records of ocean surface temperature changes, and the reason they used the ocean surface temperature proxies is that terrestrial proxies are just at this moment too difficult to use because you need to know what the elevation of the land surface was to use land surface temperature proxies. And the continents move around, and there's mountains, and so it's almost impossible to use those for this kind of project to infer the past temperature changes. So, yeah, there's a lot of data, especially for the past 66 million years, but this is the temperature data. And then they used a climate model called HAD-CM3L, and they did climate simulations at 85 time slices for the past 485 million years. And so basically there's one climate simulation to represent every 5 million years or so. And for each of these time slices, they ran 8 different model simulations with different carbon dioxide levels and other model parameterizations, just to give sort of a range of estimates of the modeled climate. And these are the 2 data sets that go into the data assimilation. Basically, after the assimilation, compared to the original modeled climate, there's a lot more variation in the global average surface temperature, and that's because these proxy data is able to sort of correct for the uncertainties in the climate model. And so one of the things is that compared to the original model data, the assimilated data is on average 2 degrees warmer, so 24 degrees versus 22. So the average global surface temperature for the Phanerozoic is 24 degrees Celsius. But also that the variations in temperature went from 2 degrees to 5 degrees in the assimilated climate. So basically, the assimilated temperature reconstruction shows a lot more variability, which is probably a lot more realistic when you think about it. And it does fit with the assimilated reconstruction, does fit with the major ice ages that happened, especially in the Carboniferous, which was 300 to 350 million years ago, and the current ice age. And it also fits with the Cretaceous being a very hot period. So the current temperatures are very much at the low end of the compared to the global average temperature, the current temperatures are quite low compared to this 24 degrees average. So another thing that they found was that there's a strong latitudinal dependence on surface temperature, and this is much larger in these so-called cold house periods. So a cold house period is when global average temperature is below 18 degrees Celsius. And when you're in a hot house period, that's when the global average temperature is above 28 degrees Celsius. The variation in surface temperature between the equatorial regions and the poles is not so much. And so one of the statistics they found from the assimilation is that the Earth has spent roughly the same amount of time in cold house and hot house periods, and the cold house periods are when there's a lot of glaciation, and the hot house periods are when some parts of the Earth's surface were probably too warm to be hospitable to plants and animals. So you don't want to be in a hot house condition for very long. Another interesting result is that in the equatorial regions, there was a 20-degree difference between the cold house and the hot house periods. And this is a bit surprising because originally it was considered that the average temperature in the equatorial regions didn't really change that much between the cold house and the hot house periods, but this assimilated experiment seems to suggest that this is not the case. So that was very interesting. The final thing that they found is that, which was also a bit of a surprise, is that carbon dioxide provides the strongest control on global average temperature during the Phanerozoic. And the reason this is a bit surprising is that the sun is gradually the sunlight is getting more intense over time. So it was originally thought that the lowering of carbon dioxide that has happened in recent times was sort of balancing out the changes in this luminosity of the sun, and that seems to be not as strong as they expected. So there seems to be a fairly strong relationship between the carbon dioxide and the global mean surface temperature. This relationship is not so strong in the Mesozoic, so they weren't really sure why this was the case, but it's possible that because the Earth's surface temperatures were so hot that maybe there were other factors which were not taken into account in the climate models that was affecting the global surface temperatures. And the thing that they concluded is that the apparent climate sensitivity to doubling of carbon dioxide was 8 degrees Celsius, which is, if you follow climate change reports, they always talk about the climate sensitivity of doubling of CO2 is usually between 2 and 5 degrees, and this 8 degrees is much higher than that, and that's why they call it an apparent sensitivity, because this 2 to 5 degree increase in temperature due to a doubling of CO2 is for the current configuration of the Earth. So what they've done is of course taken into account the changes in the position of the continents, so that also impacts what your measurement of the climate sensitivity is.
But the important thing is that based on their results, that once you start pushing carbon dioxide levels above 800 parts per million, you start to get into a warm house period. So with their results, even right now, the carbon dioxide levels still put us in the cold house state that we currently are in. But it is quite important to think that making sure that carbon dioxide doesn't go up so high will be important to ensure that the Earth doesn't face catastrophic climate changes. All right, that's the end of episode 3, and I hope you tune in next time. Thank you.
Thank you for listening to the Raised Beaches podcast. If you enjoyed this, please follow my social media accounts, where I post more information on the paleoclimate sciences. I am on Mastodon with the username @DrEvanGowan@FetiScience.org. On Blue Sky, my username is @evangowan.bsky.social. On LinkedIn, my username is Evan James Gowan. I hope you tune in next time. Thank you.